today. Jonna Roden is our first speaker from Edinburgh. She's finished her PhD, now doing a postdoc, and you're going to tell us a lot about interacting particle systems. So,
all right.
Thank you.
Cool. Yeah. Yeah. Thanks for having me, and yeah, thanks for coming, everybody. I think turnout is better than at Edinburgh, so well done. Yeah. So I just finished my PhD, literally like a month ago or so, at Edinburgh Uni, and I'm now doing a postdoc there for a year. And I'm going to talk a little bit about the things that I've been doing for the past 4 years, I guess now. So that would be modeling and optimal control of interacting particle systems. So first talk about some models, then about optimization, and most of my work actually has been on numerical methods. So we're going to talk about that, and I'll show you some pictures at the end as well. And given that this is a PhD seminar, kind of do shout, do ask me questions. I don't really know what your background is, so if you have any questions, let me know. Okay, so motivation slide. What do we have? So we have a nano-filtration device on the top left. So that's just red and white particles. They get carried through this kind of nano-filtration device and get separated out at the end. So the red particles go out at the top and the white particles go out at the bottom through this geometry. And then we have some bacteria and probably some nutrient dish or something, some blood cells and blood vessels, and then everybody's favorite example, yeast sedimentation during the beer brewing process. All of these things have one thing in common, kind of all like this. So some particles in the background fluid. And that's the type of thing we're interested in modeling, either because we want to describe this or any of the other things on this slide. In particular, what I've been interested in is modeling in processes that are inspired from industry. So for example, these nanofiltration devices are used in industry to separate out different blood cells, so red and white blood cells, or nanofiltration of algae, so that you want to separate like small biomaterial. Or if we can think of, for example, a mixture of particles going through a funnel. I mean, that happens on lots of different industrial processes, right? And you might see here this example that the bigger white particles can get stuck on the top because all the red ones kind of block the exit. They're smaller and then they block the exit. And then here, of course, yeast sedimentation and brewing. Okay, so what we're seeing is that we need to describe this with some mathematical model that we then need to solve on some geometry, because all of these things are kind of is relevant to the problem, right? Like we can't just model this nanofiltration without taking into account that we actually have this complicated channel. So we start with something reasonably simple. We're saying that we're not interested in each individual particle and what they're doing. We're interested in particle distribution, the density of particles. So rather than looking at each individual particle here, here, and here, we're saying, well, here they're uniformly distributed. Here they're kind of half and half. And here the distribution is no particles at the top, all of them at the bottom. And this particle distribution is described by rho, so that's the density. And if we start with a simple model, we're having advection diffusion. So the particles will diffuse out over time, and they will be kind of advected by this background flow field W. So for example, in the nanofiltration device, this W would be the blue arrows that carry them from left to right. And we also don't want any particles to go through the walls, right? So if we have the beer glass, we don't want our yeast particles to escape. So we need no flux boundary conditions, and they look like this. Okay, cool. So far so good, but that actually doesn't tell us much, because we need one more thing, at least. Can make this as complicated as we want, but the particles will see each other, right? They will interact, and we're just making it very easy in terms of interaction, very easy. They're interacting pairwise with like a given force. So this force is this grad V2. And then we're saying we're taking a particle rho at position x and a particle rho at position x dash, and then we compute the forces between the two. And we do that for all the particles in our domain, all the particles in our beer glass, for example. So that's an integral, right? Because we need to do that for each particle in the domain. And that can be something like electrostatics, so how they attract each other or how they repulse each other. And that's for the purpose of today, complicated enough. Make it way more complicated, you can describe way more complicated interactions, but it's already complicated enough because we have a nonlinear, right? So we have two factors rho. It's not local in space because we have to integrate. So in space, we have to look at every other process. And the term also enters the boundary conditions. So those are things that we have to take into account when we come up with a numerical method for solving this, especially on a complicated domain like this one's above there. Okay, so that's how we model particle dynamics. And if we want to model two types of particles, so the red ones and the white ones, for example, in this nano-filtration device, then we will have just two equations that look like this and a second integral term describing how the red and the white ones interact with each other as well. But I just don't put that on the slide because it just looks more complicated, but it's not more informative. Okay, so far so good. We have a model, but what I actually want to do is I want to optimize things. So in most of these type of industry applications, I want to know how can I do this in the best way possible, right? So in this nano-filtration device, I want all the particles to go out at the bottom and all the red particles to go out at the top. I don't want any white ones at the top, red ones at the bottom, right? So that's an optimization problem. How can I change my experimental setup to get optimal separation of particles? Or in this one, I kind of hinted at this already. How do I get all the particles to go through the funnel? This one. How do I get the yeast to sediment as quickly as possible so that we get our beer quicker? Because actually, in industry, it is a problem that once the beer is done brewing, we have to wait until this whole sedimentation thing has happened because, well, otherwise you have yeast in your beer. That's not maybe what we want. And it takes a long time, so we lose a lot of money and a lot of beer. So what we do is we formulate an optimal control problem. Don't get scared about all the math. This is our model. We've discussed this, but we can forget about this. What we're interested in is in this minimization term at the top. What we're saying is we want to get our particle density rho close to some desired distribution rho hat. So that's the first term there. And that desired distribution, for example, is all the particles at the bottom as quickly as possible, or all the white particles at the bottom and all the red ones at the top. So that's the desired state that we want to achieve. And the second term is something that we can control in our system. And for the problems that we're looking at for now, here today, that is the advective field. I mean, you can choose other things depending on what you can control. For this nano-filtration problem, it would be how can I modify this ground advective field to get optimal separation? For example, if I only care that all the white particles go down at the bottom and I don't care what the red ones do, then I could just say we're just doing very weak advection so that all the particles end up going down the hill, say, right? So yeah, so we're saying vary W so that rho goes close to rho hat. Okay, so that's the problem. How do we solve that? In high school, if you minimize a function, you take the first derivative and set it equal to 0, right? So that's exactly what we're doing, only we will have the derivative of this with respect to rho, the derivative with respect to w, and with respect to another variable. It's called the adjoint variable. So we will have 3 equations to set to 0. And when we do that, we get a system of 3 equations. So this is the first order optimality. That is kind of like the first derivative of f is equal to 0 to find minimum and maximum of a function. So for the first one is a PDE that we had, that is how the particles move. We have a second PDE that is called the adjoint PDE that we also have to solve. And then we have the third equation that links the 2 PDEs together. So the first thing we can do in this case, not in every case, but in this case, we can just substitute that in. So we have a system of PDEs that looks horrible, and we need to solve that somehow, right? And we need to solve that on these crazy domains. Couple of problems. Our particle PDE has an initial condition. Second PDE has a final time condition. That means that given that they're coupled together, we can't just step forward in time to solve. That's not ideal. And the other reason why we can't do that is because they have opposite Laplacians. So that means that the Laplacian is diffusion, right? So if the particles spread out, then if you do that backwards, they kind of peak up, right? So that's not great. So we can't just discretize and solve forward in time as the take home. Okay, so what was I doing for the past 3 years? I was solving the system of PDEs with all these terrible terms in them and the terrible boundary conditions on these complicated domains. And the way we've been doing this is using pseudospectral methods, which is a class of numerical methods, and with a Newton-Krylov algorithm for the optimization part. What are pseudospectral methods? Quick question. Does anyone have a question so far before we go into numerics? Yes. Yes.
Where did this come from?
So it's like a Lagrange multiplier.
And this is for the optimization only.
Yeah. So what you do is kind of gloss over that. So you have this minimization term. So this J, and you add on this PDE multiplied by Q, this adjoint operator, which is a Lagrange multiplier, and you integrate over to space and time. So that's your Lagrangian function. And that's what you take the derivative of.
This provides you with a way to minimize J.
Yeah, exactly. Thanks. All right. So, when we solve differential equations, we have to discretize, right? And normally we discretize using equispaced points. So we just divide our space up into equally spaced points, and then we do stuff. What we're doing here is we're doing Chebyshev points, which means that if you just look at the top, the points are clustered around the boundary. So they're kind of closer together on both sides and then sparse in the middle. And the reason why you do that is that you can then use interpolation methods. Normally interpolation is bad. For these points, interpolation is good. And the reason why this is good is that for smooth functions, so if you know that your function is smooth, then your method will converge exponentially quickly. So that means that you don't need many points. It's very cheap to do, or very accurate to do. So you can do that in 1D, and you can glue 2 of those together for 2D. You just tensor product 2 lines together. And then you can, well, if you have this, then you can map conformally to polar coordinates. So that's great. We know how to do that. We can discretize our PDE on this. If we know how to do that, we can glue shapes together and do more complicated things, right? So if I know how to solve my PDEs on this shape and on this shape, then I can figure out how to do it on this shape. And I just briefly show you. So rather than showing you on this complicated system of PDEs, I'll show you on this. So that's just the diffusion equation, right? I know how to discretize the PDE on each of these blocks. And I know how to discretize the boundary conditions on the red points. So the only thing is what the question that I have is what to do on this blue line. And what I do there is that I impose matching conditions. So what I'm saying is that, well, my particles should be the same on each side of the line. So the particle density should be the same. There should be not a massive jump suddenly. And also the particle flux should be the same. So whatever goes out of this shape should enter the second shape, and whatever goes out of the second shape should enter the first. So there should be some sort of continuity. So that's all I'm doing between those two shapes. So I discretize this. So I just calculate the operators on the points that I chose. Glossing over a lot of details here. And then I can write this in this form. So this is just a system of ODEs and differential algebra equations now. So M is a diagonal matrix that has zeros if boundary term or one of those guys, and a derivative if it's one of the PDE terms. And that is something, if I'm just wanting to solve the PDE, that's actually something that I can do with an ODE solver. That's not complicated. But of course, I didn't want to just solve a simple PDE like a diffusion equation. What I wanted to solve is this thing. But I can discretize it all the same. So I just need to discretize these operators on my grid. I need to do some quadrature, the integrals. And I get two systems that look the same way as for the diffusion equation, essentially, right? There's just two systems of ODE. One with an initial condition, one with a final time condition. And the way we solve these systems is that we say, okay, so if we bring those green things over to the right-hand side, the left-hand side should be 0, right? So what we're doing is we're building residuals. So we're saying this left-hand side should now be 0 if we're integrating somehow, and that's with this algorithm that I'm not going to explain because it's kind of technical. With this algorithm, we can minimize the residuals on the right-hand side. So we're just saying, given a Q and a rho at each of the times, drive these R's to 0. And if I have a rho and a Q that does that, then I solved my system and I found my minimizing solution. Okay. That was a lot at once, so let's look at some pictures. So this is the solve. And the way we're going to do this is by looking at first how we don't impose any control. So if we don't vary double, we say actually going to put any vector field on. How well are we doing? So how big is our cost functional, this J, and then compare that with whatever J will be once we did our optimization team. And we hope that the J will be smaller because we wanted to minimize that. So first, just to get kind of a view on this, I can do this in 2D on the simple domain. So here it is. So I start with a uniform distribution of particles. And then I say I want them to clump there over time. So where they do clump. If I don't impose any vector field, if I don't impose any control, the particles won't do anything actually, right? Because there's nothing to move them to that clump. But if I do impose some control, some vector field, then you can see here, these arrows, that is my vector field. They push the particles to go to accumulate in that clump. And then I can compare how expensive, like how my cost functional value would be if I didn't do anything. So if it just stayed uniformly distributed, and how far I am from the distribution of particles that I want to be at, so this clump, and compare it to how my cost functional value is when I actually did the optimization and I did get the particles to clump. It's just a way of quantifying how I'm doing. Right. Okay. And finally, we can do this on a complicated domain with types of particles. I didn't show you the equations, they're just messy. But first particle species is at the top, so that was red, I think, not white. So the red particles are at the top, the white particles are at the bottom, and they both start here, and we want them to go to the other side, right? And we want the background field, this advective field, to push them from left to right and send them out. Yeah, and that's what we're doing. So if we didn't impose any control, all the particles would stay on the left, right? Because nothing pushes them to the right. We can evaluate what the cost of that is. Then we do optimization, and we find that indeed we do push them to the right-hand side, and we do separate them in some way, and we have a less expensive, well, the cost function all goes down. So that's exactly what we want. And I think, yes, that's all I kind of wanted to tell you. Yeah, I glossed over a lot of details, of course, because we have 20 minutes, I think. But yeah, so this is just one way of solving these nasty PDs that describe particle dynamics on these complicated domains, and doing the same thing for the problem, right? And I think, yeah, so we've done a lot of work on the numerical methods that I kind of just hand waved over, but I'm happy to talk about. But I think there's lots of interesting stuff still to do, applying these to different type of problems. I just illustrated a couple of them. For example, what I'm doing now is applying this to opinion dynamics models. I think some of you have heard of that as well. So yeah, cool. Any questions? Maybe not.